My name is Slav Petrov, and I'll be talking about some stuff that I've been doing with my advisor, Dan Klein. The goal is going to be to take sentences and produce parse trees for them. And we'll assume that we have, we want to do this for many reasons that I don't need to explain to you. And we'll assume that we have a bunch of labeled examples, a tree bank that we'll start from, and then we'll try to learn a context-free grammar. And I'll be talking first about how to learn the grammar, and then the second part of the talk is going to be about doing efficient inference. So the problem or the challenge in designing a grammar for parsing is that the categories in the tree bank are too coarse to model the complex underlying process. For example, if you look at those two noun phrases that we have in this sentence, one is in subject position and the other one in object position, and they have very different distributions. So in order to design a grammar that captures these phenomena, you need to refine the observed categories. And typically this has been done in kind of manually by either doing structural annotation in form of parent annotation. For example, if you know that the parent of this noun phrase is the sentence symbol, then it's very likely that this is going to be the subject noun phrase. And if the noun phrase is under a verb phrase, then it's probably an object. Another way of capturing this is by lexicalizing the grammar, where you propagate information from the bottom up in form of head words. This causes the grammar size to get much bigger, and you need sophisticated smoothing techniques to deal with sparsity. In this work, we'll try to do something different, where we say we have k numbers of categories, and we'll try to learn automatically what these categories are with the EM algorithm, clustering them into hopefully meaningful categories. We'll start with the bare bone structure of an X-bar grammar, where we have just the observed categories in the tree bank, and we'll keep refining the categories in a hierarchical way, allocating the complexity only where we need it. So after this introduction, the first part is going to be learning what we want to do. Okay, there's some previous work in this. My advisor, when he was a grad student at Stanford, spent a bunch of time refining those grammars, first by annotating them with structural information in form of parent and sibling annotation, and then manually doing kind of an EM-type hill climbing, where he hand split the categories into linguistically meaningful subcategories and checked whether this helps actually improve parsing performance. But after a while, the performance started to level out because he started running out of ideas. And this is a very tedious process that has to be redone for every language. So it couldn't be scaled up to parsing any arbitrary language. Then a few years later, and so starting from a naive tree bank that is just read off of the tree bank, you can get up to 86% parsing accuracy, where state-of-the-art is about 90, 91, nowadays 92. And then a few years later, there was some work on automatically inducing these subcategories, where each category is split into k different versions, and the EM algorithm is employed to learn those categories. But the problem with this approach is that because every category is split into the same number of subcategories, for binary rules like this one, the number of parameters grows cubically in the cardinality of the latent variables. And so you quickly reach the limits of what fits in memory, and parsing is very slow. So what we would like to do, but they achieve the same performance, roughly. And what we would like to do is take the best thing of both worlds. We would like to allocate the splits only where we need them, but automatically learn where to allocate them. And the resulting grammar should be compact and capture many of the features that are present in the data. And everything should be done automatically so that we don't need a linguist to sit down and specify those categories. How are we going to do this? Well, we'll start with these parse trees. And the first thing to note is that because the brackets, the whole structure is observed, and the base category is already observed, we don't need to run the general inside-outside algorithm, but we can instead run a simplified version that is more like the forward-backward algorithm for HMMs. We do one pass up and then a pass down, computing inside-outside scores that are restricted to conform with this observed structure, so that the algorithm is linear in the number of words rather than cubic, and therefore very fast. If we do this, we can start with a grammar that has about 100 categories, and then when we have 2 subcategories per category, we improve from like 64 to 76 and keep going. This is what previous work did, and at some point we run out of memory and also patience to run it. So when we have split every category in 16 substates, performance levels out at about 86%. And our contributions will be threefold. We'll present a hierarchical training scheme that allows us to converge to a better local optimum, because EM is a local method and can get stuck in a suboptimal solution. We'll do the splitting in an adaptive way, where we allocate the splits only where needed. And finally, to prevent overfitting, we will smooth our parameters. And this will lead to state-of-the-art parsing performance on a variety of languages. So,
is it okay to interrupt?
Yeah, yes, please.
So when you do the splitting of the labels there, and you measure label precision and recall, do you map them back to the original label?
Yeah, so the easiest thing you can do is to just strip off the hidden state. We can just do Viterbi decoding and then just erase the labels. In the second part, I'll be talking about inference, and it turns out it's better to try to marginalize out this hidden annotation. You cannot do it exact because it's NP complete, but there's a variational method that gives good performance, but I'll talk about it in the second part. So we're just interested in recovering the observed categories. The hidden categories that we induce are just going to help us model this better, but we're not interested in them per se, though they are linguistically interpretable, as I'll show. Okay. So actually, there's the first example. If we look at what happens when we take a category, determine a category, these are the 3 most likely words when the category is unsplit. And when we go to a grammar with 4 categories, we might end up with something like that. This is a real example. When we want to learn a grammar with 8 categories, the way we currently do it in this naive version was to just start from the same one and try inducing all the categories at once. But what is much better is to take the category, split it in 2, and then take each of those categories, split it in 2, add a little bit of random noise, and run the algorithm initialized from this previous local maximum. So this minimizes the number of training iterations that you need to do, and it turns out that you converge to better local optimum in terms of log likelihood and also in parsing accuracy. And what is nice about this is that the splits that we learn, they very often emerge in the same way. So here we have learned that the determinant category, in fact, has determiners, but also demonstratives in there that are linguistically somewhat different, and they tend to occur in different situations. And this split occurs always at first. And then when we go one step further, we learn that there's indefinite and definite determiners, and that there is demonstratives and quantificational elements. And those patterns are often observed that the categories that we learn are linguistically sensible. Sometimes they're syntactically motivated, sometimes semantically, often there's a mixture of both. So if we look at parsing performance, we see how at the beginning, both methods are exactly the same, but then already with 4 subcategories, because we initialize the position, we tend to converge to better local optima, and parsing performance increases by about 1% when we do this hierarchical training. But no matter whether we do this training in a hierarchical way, splitting some categories is just silly. For example, there's a comma category, and there's no point in splitting it. Those trivial examples can be captured by hand, but then oversplitting will occur eventually for any category as long as you keep splitting And for example, we can look at the determiner attack again, where I've just zoomed in on the left branch. We have the indefinite and definite determiners, and then when we go to when we do one more split round, we see that we end up with two categories on the one side where we have sentence initial and sentence medial distinctions. But then these two categories look quite similar. You might say they're the same, and this is already oversplitting. We don't really know what the underlying statistics are, so it's kind of hard to judge from a human perspective, and we don't want to have a human in the loop. So we would like to have some way of splitting the categories and evaluating how good the split was. Because it is very hard to say which category to split next. We follow this approach where we split everything and then revisit it and merge it back. And so for this thing, we might say, well, these categories, they don't contribute much. We want to merge them back. But other categories might survive. So something wrong with my animation? Okay, yeah, so we'll split. We'll look at the split and then merge it back. This split on the other side, we might keep it. So that we'll have, rather than a complete split tree, we'll have kind of this rugged tree. And the way that we'll evaluate how useful the split was is by a simple likelihood ratio, where we compute the likelihood of the data with the split reversed over the likelihood of the data without the split. And we'll do a simple approximation where we just we compute the likelihood locally just for a given node in a parse tree, so that we don't need to reparse the whole training set. And this gives us then a controlled way of deciding how many of the splits to keep. We can sort the splits by their likelihood gain and reverse a fraction of them. And we found that if we reverse half of the splits, we don't lose much in likelihood, and we don't lose anything in parsing accuracy. So we fixed it at 50% and didn't really experiment more on this side. When we,
I understand that. So when you reversing the 50% of the splits that have the lowest
least contribution to data likely.
So that's the question so when you have hierarchical splits, mm-hmm. I mean, you can think about this as having, when you have your level 2 and 3, say, splits like you had there, the sort of the split on the left and the split on the right don't have the sort of the same meaning necessarily, right? Yeah. So, I mean, another view of doing something like this is rather than thinking hierarchical splits, is thinking adding individual bits. Now you have 4 possibilities. You know, you have one possibility, then you have 1 bit, 2 possibilities, and then 4 possibilities at the bottom. And then you may decide which bit is least gain, and then you merge that back. That's slightly different. Would it be better? Would it be worse?
We have some consequent work on discriminative parsing, where we treat each split as an independent feature. And there you can, you induce these features, and depending on the context, we don't explicitly merge them back, but you might just say, well, I want to have the feature for the global one, and for this category, I don't care about this particular split. And depending on the context, you might want to condition on a lot of features, and in some other context, you might go back to the very general category. Mm-hmm. I haven't thought about it too much in the generative case. What we did try was to kind of enforce, rather than just letting each category, each thing be split independently. When you think about, so these are lexical categories because it's easier to display, but when you have binary rules, you split, especially, so to get binary rules, you take an n-ary rule and you binarize it, and you have this backbone structure. So we tried fixing particular bits along the backbone because we thought that we want to propagate information along the whole backbone. And it turned out that restricting the grammar in this way hurt performance. It seemed to be better to just let EM do its own thing.
So when you do the splits, do you add some perturbation to the distribution?
So we take this, we create 2 copies, and then we add 1% of random noise to the parameter, and then we run EM.
Because this is very similar to growing a decision tree in many ways, right?
Yeah, but
so I was just wondering. And also when,
so
when you said you rank them by how much they change the data likelihood, is that the training data, or you have some held out data for that?
We do it on training data. We could use held out data, but it seemed to work fine with the training data. In fact, we experimented with a bunch of different ways of kind of merging things back, and it seemed to be quite robust. Like the same kind of splits tend to emerge. If you merge too much back, you end up hurting your parsing performance, but then in the next round you introduce the same split again. And so you're kind of doing the same work over and over again. And so that's why we fixed it at 50% where we don't lose any parsing performance.
So just a quick question.
Yeah.
You mentioned that you've done this thing about trying to somehow tie these variables together. So what kind of constraints? How did you specify what constraints?
Well, we just said, well, like this category, like 1, 2, 3, 4, you can just interpret them as like a binary, like you have two binary features, and then you just say the first, like the odd features cannot change along the backbone of of rules that have that are coming from binarizing a bigger rule.
So it's like passing features of the head.
Yeah. And we experimented also with head binarization, right-left binarization, and it seemed that just doing simple right branching was fine. Though the branching direction seems to matter a little bit for some other languages. But yeah. Okay. So if we look at parsing performance, what happens is that we don't lose anything in. If we look at number of like split rounds, we don't lose anything in parsing performance. But what we can do is that we can now do 2 more iterations of splitting, so that some categories get much more refined, and this improves parsing performance by another %. However, what you might now start worrying about is that at this point we split some categories into up to 64 categories, subcategories. So we can look at it, and for the phrasal subcategories, we see that every category, for every category, some splits have been reversed. So it seems like we're reaching a point where performance is going to level out, even if we did more splits. And also what is interesting to note is that the complexity has been allocated in a reasonable way. Categories that are frequent and have a lot of structure have been split a lot, while other things that are either rare or don't have a lot of variation because they always produce the same thing have not been split much. And in the lexical categories, we can also see that the most heavily split categories are the open classes of like nouns and adjectives. And in fact, the proper nouns have been split into 63 subcategories. So even there was a merge.
Yeah. Does this include the any manual splitting? For example, you mentioned comma was.
No, there's no manual thing. This automatically learned that commas should not be split because they always produce the same thing. There's no gain in likelihood if you split them. But in work that I've done since then, we have actually scaled it up to do 1 or 2 more split rounds, and performance has leveled off. So it seems like we've extracted as much of the data of the structure as there is for this type of model.
Are you also getting something like the parent annotation,
yeah, so I'll show some lexical examples, and there is a bunch of examples in the paper about kind of structures that how you learn how to propagate parent information. But they're kind of hard to analyze because there's so many things going on in the grammar. So we have a small interface where you can click through parse trees and rules to see how things propagate, but it's kind of hard to analyze. But what I wanted to allude to is that one problem that this model has is we're taking these observed categories and splitting them in a large number of subcategories. So this heavy splitting can lead to overfitting, because now we have these 64 or 63 in reality independent categories that are treated as just completely separate symbols of the grammar. There's nothing saying that all these things are proper nouns in the model. So one way of tying them together and sharing statistics is to do what we call parent smoothing, where the parent is now not the parent in the tree, but the unsplit category. And we experimented with different ways of doing this, but it turned out that it doesn't matter how you smooth, it's important that you smooth. So a simple linear smoothing where you just have one parameter which is set to 0.1 and says that you believe to what your statistics say to 90%, and the rest comes from your siblings. And we do that after each round of EM. We compute new maximum likelihood parameters and then smooth them towards the parent. It gives a lot more robustness. So when we look at the result, yeah?
One question. I mean, there you're showing splitting and non-terminal, but in a way, you're really splitting rules.
Well, so, yeah, I mean,
so
in the rule...
So how does the shrinkage,
so
marginalizing overall latent size?
So what we do is we just look at the parent of the rule. So for a fixed parent, AX, that's like the X is the subcategory, we take all the siblings of the, like for a particular configuration of these, we take all the other combinations. So they're tied to the head of the rule. So all rules that have, like there's a Y and a Z here, like there's subcategories for the B and the C. But so there will be, yeah. So for all those rules that have AX on the right, on the left-hand side, and some type of B and some type of C, they will be smoothed together. Is there something to draw? So the rules, so if we have A0 goes to B0, C0, this will be smoothed with all rules that go. A0 goes to BX, CY. They will be put together. Like the parent is kept fixed, and then all the siblings.
I'm sure I'm convinced by that. So maybe I'm mistaken.
Convinced that it's makes sense, or
yeah, right. So, what I want to do is this is smooth to a less specialized rule, right?
Yeah.
But the less specialized rule, when you split a non-terminal, you also effectively have to split the other ones to take any advantage of that split.
So, I mean, what we could do is we could smooth towards the kind of the completely unsplit rule.
Yeah.
And I don't think we tried that. We always did. So for the lexical categories, there's no difference because I mean there's just one production, and then for unary and binary productions, that would make a difference. So we could average out the whole thing, but we always did this.
We can talk about it later.
Yeah, could be better. Yeah.
The smoothing here is only for the left-hand side, right?
Yeah, so that's what we were trying to.
Right, but you don't. Do you always smooth the right-hand side, or you only do in this?
No, we're just doing this, but the idea is that when so you're trying to build a constituent over something. So if you just smooth over like the left-hand side, kind of when you compute the score of the left-hand side of the parent, like the smoothing will have taken effect. So when you combine that with something else, like it's already, the parameter for this constituent is already going to be smooth. Like you don't need, like otherwise, if you started smoothing more, you would start like kind of double smoothing.
So is it like you have like MP0, MP1, and then you have like different rules for MP0 and MP1. But once you build this, you always treat them, like use this in something else, you always use them as MPs, whether it's MP0.
No. We keep them as MP0. So maybe I can write on the board.
There's
or there's the chart. So when we start off with a rule S goes to VP, NP, VP, there'll be some parameter P. This is the unsplit rule that is in the Treebank. So what we create is then S0 goes to NP0, VP0, and then S0 goes to NP0, VP1, and then 1, 0, kind of all combinations, and so on. So in the first split, when the categories are split in 2, we split the rule into 8 things. And when we apply the smoothing, we will smooth those 4 and those 4 together. And where we say, well, if you want to produce an S0, it is important what type of NP and VP it is, but it is not like, there should be some, I mean, the smoothing kind of makes them a little bit less different. So you're more tolerant, like you're willing to, when you construct this S0 from NPs and VPs, you want to kind of share statistics across the right-hand sides. So you care about what particular parent you have, but you're a little bit flexible on the right-hand side because you know that when you have a lot of splits, you'll be fitting noise and overfitting your data. So, and then that's why we just split on the left-hand side, because we say, well, the next time, wherever S0 is on the right-hand side in some rule, it's going to get smoothed there. Because we're applying it always to the right-hand side, so we don't need to smooth. Like we could smooth the whole thing together, but this way we kind of have a little bit less smoothing and a bit more control.
So these have to be proper conditional probabilities, right?
Yeah, yeah.
And that happens.
Yeah.
Okay.
I mean, yeah, we just do it in a linear way, right? You start off with something that sums to 1, and the next time it's going to sum to 1 as well. And if we look at performance, we see that at the beginning, when you have just 2 subcategories and things are truly distinct, smoothing actually hurts you a little bit because you're just trying to separate them, and with smoothing you put the things back together. But then towards the end, you gain 1% in accuracy in a bit. And yeah, so at the time of the paper, we couldn't do more splits, and it looked like the gap is getting bigger and we can go even further. We scaled it up, and unfortunately, it just leveled off. But it is also interesting to see for other tree banks, so we have run it on other languages since then, where you have less training data. So this is for English, where you have 1 million words. For German and Chinese, you have 300,000 or 500,000 words. Performance actually drops off here, and if you don't do smoothing, it actually starts dropping because you're overfitting. So the smoothing is crucial, but doesn't, yeah, we tried different ways, and just the linear way works fine. You just need to do it.
How many smoothing parameters do you use? Just one for all the rules? Or?
There's, I think in the current version, there's 2. There's one for the rules and one for the lexical productions. But at the beginning, I think these numbers are with just 1. Like we try to keep as few parameters free as possible.
And that's also learned via EM?
No, that's manual. Just like we tried 0.01, 0.1, and 0.2, and 0.1 worked fine, and we fixed it and left it. So some examples of what is being learned. We see for proper nouns, we observe things like months, first names, middle names, last names, then what goes first and second in compounds. For the personal pronouns, we learn casing. We have some nominative and some accusative personal pronouns. Like,
I noticed the title of the slide, sorry.
Yeah, it's you can argue that it's just, yeah, how useful this is, but it is nice to see that the things that you learn are actually interpretable and linguistically meaningful. And when you look at the rules, you see that many of the things that my advisor did as a grad student by like manually splitting things in linguistically motivated ways, they emerge naturally.
Just fire them in the Sorry.
Yeah. Yeah, I should go to give the talk to Jenny.
You should have said that.
And I'm more of a computer scientist than a linguist, so I guess that was good. Okay, so now that we have talked about learning, we should think a little bit about inference, because one thing that I omitted, because it was not really favorable, is that parsing the development set took about a minute per sentence. And so if you want to do parsing in any type of application, this is useless. So we need to think about how to make it faster. And the problem is that even though the grammar set is small in the number of categories, because the number of parameters grows cubically, they're very densely connected, and you need to sum over many things, or max over many things when you're doing inference. So we'll borrow some ideas.
So, a quick question. So if I contrast the grammar you produced as a result here with a grammar produced by, say, with the various by Collins or Charniak parse, and what's this relative size of the grammars in terms of actual rules?
So I think it's roughly the same as Collins and Charniak's because of the lexicalization, which makes things like lots of parameters, so that you need smoothing. But our grammar is kind of slower to parse with, because you have fewer constituent types, but the same number of parameters. So when you want to construct a constituent, you need to loop over many things. But in the lexicalized grammar, you know the head word, so you just have this one particular constituent that can go there. And so that's the problem with this kind of approach. Though, in the meantime, the discriminative grammars that we have, they're orders of magnitude smaller, so that you end up. So this thing has around 1 to 2 million parameters, and the discriminative ones have like 50,000 parameters only, and have the same parsing performance. But that's not going to be part of this talk. But I can talk about it later. So we'll borrow some ideas from previous work to speed up parsing inference, and the main idea is coarse-to-fine parsing, where you take your tree bank and you estimate a refined grammar. For example, the previous work used lexicalized grammars. In our case, these grammars will be just split grammars. And then in addition to that, you have a coarse grammar that is much more compact and fast to parse with. The only thing that you then need to do is establish some type of correspondence between the symbols of these grammars. For example, saying that we can just strip off the lexicalization, or strip off this hidden annotation in our case. And then we'll parse with the coarse grammar. We'll compute the posterior likelihood of constituents and prune away unlikely constituents, so that when we parse with a refined grammar, we can skip over many types. So this is a pruning heuristic. It's not guaranteed to give us the correct result according to our model, but in practice it works really well. And like you have a threshold that you need to set for each. So we have a global threshold that we use for kind of all pruning passes, and we set it by tuning it so that on a development set that we parse, we don't make any parsing errors. But we don't know whether this means that we don't make any parsing errors on the real test set. And what we do is we go through the constituents, compute the posterior probability, and then if we have, like we might say QPs are very unlikely, but NPs and VPs are likely according to the coarse grammar. So when we go to the refined one, we can just skip over the refined versions of the QP, the quantitative phrase. So this idea, if we apply it, allows us to cut down the parsing time significantly, but we are still too slow for practical applications. However, what we can do is we can do it in a hierarchical way. We can, instead of going from the coarsest version to the most refined one, we can do several rounds of pruning. We start with the coarsest one and then prune away one symbol. Then we go to a grammar that has two subcategories, and there we can split already over skip over these symbols, but we need to compute the probabilities for NP1 and NP2. And we might say, well, NP2 and VP1 are not very likely, so in subsequent passes, everything that's a refined version of those categories can be skipped over. And we can keep doing this until we have reached the final parsing model, where we then do exhaustive parsing but just using those symbols. One question that arises is where to get the intermediate grammars from. One thing that comes immediately to mind as well, in training, we're producing them already. We're splitting each thing iteratively, so we can just keep them around and use them for pruning. And in fact, it works quite well. Okay, there we go. Again, with the threshold tuned so that we don't make any search error on the development set, we are down to 35 minutes now, and this becomes reasonable. But we can do better. And the realization here is that when we train things, we initialize each round with the previous grammar and add a bit of random noise. But then we let things drift. There's nothing constraining them to be the new subcategories to be refinements of the previous category. So we initialize, we add noise, and then we just keep doing EM, and then we end up with something where, for example, this the word these, there was the second highest word here, has now drifted and become a subcategory here with the dominant tag. So if we use the previous grammar for pruning, we need to be more careful and kind of with setting the thresholds. If we had grammars that are approximations of our most refined grammar, then we could potentially prune more. And one way of obtaining these grammars is by projecting back the most refined one. So we take our initial grammar, we do our learning procedure, but then instead of keeping the intermediate grammars, we throw them away, and we compute projected versions of our most refined grammar that are as close as possible, given the smaller set of parameters, to the most refined one. And this will allow us to prune, to tighten the threshold, pruning threshold, and prune more. So how can we do this? Well, to decide on the non-terminal set is very easy. For example, if you have a grammar that has been split in two, the projected version, one of the projected versions, we'll have several, it can be, for example, just stripping off all the latent annotation. And what is trickier is how to compute the parameters of this coarser grammar. And the problem is that we want to take all these rules and map them to a smaller set of rules, and we cannot just add these parameters up because we need to know the kind of a weighting for the left-hand sides. We need to know how frequent S1 is relative to S2 so that we can do a weighted combination. And the way to do this is by kind of estimating the grammar. Rather than from a tree bank, we can estimate it from an infinite tree distribution that is induced by our most refined grammar. And it looks kind of complicated, but what it boils down to is that we need to, instead of just counting parameters, since we don't have the real grammar, it's just an induced tree distribution, we need to compute expectations over these rules and over their left-hand sides. And there's a simple recursion where we start off saying that the count of a symbol up to depth 0, C0, so is 1 if the symbol is the root symbol and 0 otherwise. And then at depth I plus 1, we can recurse to taking the counts from the previous depth and then kind of expanding the tree using the rules in our grammar. And this gives us expected counts for symbols up to a certain depth. If we run this process for a few rounds, the fixed point equations converge pretty quickly, and after 25 iterations, they're quite stable. And in fact, most trees in the tree bank have a depth of at most 25, so it seems to have captured this property of how long the sentences are. So then we can use these expectations or counts to compute the rule probabilities of the coarser versions. When we do this, we can tighten the thresholds without making a search error, and they're down to 15 minutes. And this is 15 minutes for 1,500 sentences. It's a couple sentences per second. And in fact, if we're willing to make a small error of like 0.1% in parsing accuracy, which is like error on 3 or 4 sentences, we can cut this down into like 7 minutes, which is 4 or 5 sentences a second. and now becomes practical. If we look where the time is spent, we see that now the first pass with the coarses grammar is actually the most expensive one, and if we really wanted to fine-tune it, we could compute even more abstract versions of the original grammar where we conflate the observed categories and say, well, noun phrases and verb phrases are very different in some sense, but for a kind of a core structure, they might be sufficient if, and behave similarly, and compute even more abstract versions and speed this more up. But for now, this is what we do. We can visualize this process where we look at the bracket posteriors. Black means that a constituent spanning kind of over the triangle that's underneath it is likely. We're summing over the type of constituents. And so after the first pass with the simplest grammar, we see that many things are already ruled out. And the grammar says, no, it's impossible to put something over there. The span, particularly when there's commas involved, they're a good hint of whether a constituent can span over this. And then when we do the pruning in a hierarchical way, there should be a video of this coming up, hopefully. Well, okay, there's the money. So we start, and then we see how certain regions of the chart get pruned away and sparsified, and at the end, the final chart is extremely sparse. There's some ambiguity still preserved. For example, how this phrase here is at which level it attaches. But most of the other things have been already sorted out. And so even though the grammar is big, we have kind of achieved this. What the lexicalization also does is that over a certain span, we're relatively certain about what type it is, but not like there's just some small variations possible, so that then we can do the final pass where we do our variational approximation and compute the best tree. Yeah?
Just to understand this, each so there are a sequence of models, right? So
yeah.
The chart is passed on, right?
Yeah, the chart is passed on and kind of expanded because you have more kind of variation. But the nice thing is that, yeah, many of the things don't need to be expanded because they are already ruled out completely. So in each subsequent pass, you don't need to do that much work anymore.
Do you apply the same pruning threshold at every level, or have you
there's a different, so if you do, you could do the same one, but I actually fine-tuned it so that at each level you do a slightly different one. It seems at the beginning you need to be a bit more generous because you don't want to, the grammar is just very bad, so you don't want to prune that much. But then in later stages you can be actually quite aggressive because the grammars are good enough, so to say. One part that I'm not going to be talking about too much, as I see, because I thought I wouldn't have time, is what your question was, what do we do with this hidden annotation? What we're interested in is parse trees over these coarse categories, but what our grammar gives us are so-called derivations over these split categories. And so there can be many derivations that correspond to the same parse tree. And in practice, we would like to sum out the hidden variables, but we cannot because this is NP-complete. And there are different things that you can do. One thing is to just do viterbi parsing and settle for the best derivation, which works okay, but it's not the best thing, and you shouldn't probably do it because the other things are simple. A better thing is to extract an n-best list and then compute the exact likelihood of those trees and re-rank them. It helps a little bit, but the best thing is that we have found so far is to do kind of a variational approximation to the posterior distribution for this given sentence. So that you kind of construct a sentence-specific PCFG that gives you probabilities over these constituents. And in practice, it just turns out to running inside-outside and then one extra pass. That is very quick. So it's not slower, but it makes about a 1 to 1.5% difference, and is crucial for getting state-of-the-art performance. So final results in terms of efficiency, we compared to Charniak and Johnson's parser, which is arguably the state-of-the-art parser on English. We are a little bit faster. We are a little bit more accurate, and our parser is in Java rather than in C. So it's, if we ported it to C, it would be probably even faster. In terms of accuracy, comparing to the generative component without the re-ranking, because the re-ranking can be applied to our stuff as well.
Is the alternative objective similar to the Goodman paper?
Oh yeah, yeah, okay. Yeah. So it's kind of like the maximizing recall, but yeah, exactly. So for English, we're doing better than the generative component, and then if we re-rank our trees, we end up with about the same performance as they end up. The thing is that because we do so much pruning, our and best lists are not better than theirs, since we have pruned away many of the kind of almost right trees. But one of the beauties of this approach is that there's nothing that's English specific in here. There were very few parameters in it, and in fact, we can just keep them fixed and run the model on any language that has a tree bank. And the hardest part of this experiment was getting the tree banks and the licenses. But then once we had them, we ran it on German, and we outperformed the previous state-of-the-art model by a lot, mostly because there has been just much less work on German. And on Chinese, we also do much better than the previous work. We have run it in the meantime also on French, and I'm going to run it on Arabic in the next week. And on French, it's also better. So it seems to be a kind of generic approach that works well for a variety of languages that have very different linguistic properties. So some kind of, not future work because it's already in the past, but some work that we've done in the last year to extend this is to use the same idea to learn structured models for phone recognition. You can start off with simple phones, and then instead of splitting them manually into triphones and clustering them, you can just try to induce the structure, and it works fairly well. We have done a different version of this where instead of doing the split and merge heuristic, we had an infinite model with a sparse prior. And unfortunately, even though it looked nicer on paper and in the math, it is slightly worse in performance, but it's a kind of a cleaner model. And currently, I'm working on a discriminative version, which at the moment is as accurate, but an order of magnitude sparser. So to conclude, I talked about split and merge learning of hidden structures, and I showed a hierarchical training procedure that allows us to do an adaptive splitting, and combined with parameter smoothing gives very good accuracies. And on the inference side, we talked about projections of these models to coarser versions to speed up the parsing, and about marginalizing out the hidden structure. I just had one slide on that. And it works for many languages. So the parser is on our webpage, and if you want to play with it, you have to do so. And yeah, if you have questions. That's my old vision side. I like to show images.
So I have a question. So the categories that you have in the beginning, how good do those have to be? Did you ever try to throw away some information and then just rediscover what's in there? In the extreme case, if you just have the parse tree and the non-term is called X, can you?
Yeah, good question, and it's something that I've been meaning to do. I've done only the extreme case of erasing everything and just having X's everywhere and trying to recover bracketing structure. The problem that I ran into there was that the grammars grow very quickly since they're cubic in the number of the latent categories. So, and because they were so densely connected, there were kind of too many things going on at the same time, and it converged to just some very poor local maximum. So I think you either need a sparse prior or you need to initialize it with a little bit more information. One thing that I wanted to try to start kind of conflating categories that are rare or similar and see how much we could damage the grammar without hurting parsing performance, and then later also what types of other structures we can learn, because I'm interested in using this for machine translation, for example, and I'm not sure that the categories that linguists have specified for the English tree bank are the optimal ones for machine translation. Maybe we can learn some more useful ones automatically. But yeah, that's future work. Yeah.
Okay. The related question is, how much can you cripple the tree bank annotation and still?
Oh, you mean just like put noise in,
yeah,
or
not have certain type of labels or certain.
Well, so that's what I was just saying. That I have done only the extreme experiment of erasing everything, but I would like to see how much we can actually damage it without losing parsing accuracy. But that's something that I need to do.
So, two questions. So, first, it always sort of bothered me that you never learn English by reading the Wall Street Journal, right? So why not train your model first on very short sentences with extremely simple parse trees, and then from that grammar, go to more complicated sentences and try that sort of incremental training and see whether things change at all or not. Is that something that's been tried, or?
Well, there's work on kind of self-training for parsing, and the result there was that if you take a parser, train it on the tree bank, then parse a bunch of sentences and use those as your training data, your parsing performance suffers because you're kind of reinforcing the errors that you make. But if you have a parsing component and a re-ranking component, then you can parse external sentences, re-rank them, and train your parser on that data, and then it actually helps because you're having the additional information from the re-ranker that kind of feeds back into the parser. So that's some work that Charniak did at Brown. But you needed to parse a lot of sentences, like millions of sentences. But yeah, kind of a bootstrapping approach, especially for resource-poor languages where you don't have such a big tree bank. That'll be something interesting to kind of explore.
My question was strictly within the realm of the tree bank. You could split the sentences according to length and train first on the very short sentences, take that grammar, use it for...
I don't think it would help much. I mean, you might converge to a better local optimum because, EM is local search, but...
So going back to the earlier question, right? So if maybe what's happening when you start with all X's is that you're just overwhelmed by the complexity of those sentences. If you started with short sentences, maybe you made a few splits like, oh, I discovered nouns and verbs, say, right? Yeah. Without being overwhelmed by the complexity in which they are embedded. And then once you've done that, you kind of move in a better
Okay, yeah. If you're trying to learn the categories in the first place, if you don't assume that they're already observed, then yeah, I think that might be a good way to go.
And the second question was, does this have any promise? So everything here is the tree bank is very well formed sentences, sanitized text, and all that. But the real world is a little different, and I'm wondering, whether this has any promise in adapting a parser to some data that is not so close to the tree bank.
So one thing that we want to do soon is in collaboration with ICSI to parse speech data and to see how it does there and whether we can adapt it to kind of do syntactic language modeling for speech. And then I guess in the fall when John Blitzer comes, he's very much interested in domain adaptation, also just parsing biotext or some other text that's out of domain, because typically performance goes down a lot. But we haven't tried much in that direction yet.
So another question is, so you did the phrase structure grammar, right? Did you consider doing similar thing for dependency grammar? And why
I haven't done anything on dependency grammars. I guess kind of the philosophy, my advisor's philosophy is that you can extract dependencies from a constituency parser, and in some early experiments, the dependencies extracted from the Charniak parser were better than the state-of-the-art dependency parsers. So if you want dependencies, just use this and extract the dependencies off of it. But it's kind of a bold statement. And dependency parsing is typically much faster, so I'm not completely opposed to it, I just haven't done it. Thank you.